Hello, everyone. Welcome to Stat 310, Lecture 18. We're kind of now in Chapter 11, which is which involves two sample comparisons. When you have kind of samples from two potentially different populations, and you want to kind of compare these populations. And we're gonna finish that discussion on two sample comparisons, and in particular look at a specific case of that, another different sort of and specific case where you have paired samples, which is in 11.3 of the textbook. So I guess like we're kind of, I would say, in sort of the home stretch of the course, in the sense that I'd say the real like main sort of meat and challenge, and the main concepts of the course are really derived in chapters 8 and 9. That's where we kind of really laid the foundation for both estimation, confidence intervals, and testing. And now, really, what we're focusing on is specific examples of where we're going to apply a lot of the concepts that we already know, but to some specific examples. And so, the first example we're starting with is we're kind of moving beyond. So, the idea is also we're just moving beyond independent samples. So, we've started with like all of our theory and methodology that we've developed so far has really focused on the case where you have one independent sample, and one independent and identically distributed sample, and then you want to do some kind of testing or estimation in that context. But now we're going to start to move to settings which often arise in practice where you have more than one sample. And chapter 11 kind of starts with that, with when you have two independent samples rather than just one. So the setup is you have x1 through to xn, and then y1 through to ym. They're independent samples, and so you could think about many scenarios that I spoke about in the previous lecture. For example, like you could think about data from two different states, so they're two different populations, maybe California and New York. You could think about a scientific experiment with a control group and a treatment group. So they're, again, kind of, in principle, two different populations. And you want to say, I guess, there's the question of how these samples are different or similar. And then the kind of the follow-up question is, what does this say? What does this say about the populations? Okay, so we have these two different populations, and we want to say something about how similar or different these two populations are. And so the example that we used and that we're going to stick to throughout this chapter, because again, the normal example is very, very nice, and it makes calculations tractable, and again, it lays a lot of the foundation for what we see with other setups, is that we have the x's and the y's are both normally distributed, and the x with mean mu x and variance sigma squared, and the y with mean mu y and variance sigma y squared. And we started with a case in the previous lecture where the sigma x squareds and sigma y squareds were known. So in that setup, we spoke about this. You can actually derive the overall distribution of, if you're interested in the difference between mu x and mu y. The key statistic to look at is just x bar minus y bar appropriately renormalized. So when you subtract off the mean and then divide by the overall variance. This should be sigma y squared over m. Then this is going to be normal with mean 0 and variance 1, okay, where x bar and y bar are the sample mean and the sample mean for x and y. And so the question that we're really interested in is is mu x equal to mu y, or how far apart are they? So as we discussed in chapters 8 and 9, you can always propose any kind of estimation or confidence interval question in terms of a hypothesis test. So, we're going to start with the hypothesis testing angle, but I'll also talk about the perspective from confidence intervals as well. So we have, H naught, which is, mu x equals mu y, or equivalently mu x minus mu y equals 0. And then there's, a bunch of different alternatives. So if we look at H1, there's, the standard two-sided alternative. Then there's the two one-sided alternatives. Okay, and you can equivalently write these in terms of the parameter mu x minus mu y. Great. So that's so the way to think about it is that the parameter of interest here, the parameter of interest is the difference, mu x minus mu y, and then the statistic or estimator is x bar minus y bar. Okay, and so clearly we know that, from earlier calculation, we have that okay, so we also know then that under H naught, which is that mu x minus mu y equals 0. Then we have I'm going to use this notation z, which equals to x bar minus y bar. This thing's normal 0, 1. Okay, and so we're gonna, if we have a hypothesis test of size alpha, and this is, equivalent to, as we learn in chapter 9, 1 minus alpha times 100% confidence interval for mu x minus mu y. Okay, so then we have that for alternative 1, which is, H1, which is mu x not equal to mu y. So this is a two-sided alternative. Then we can kind of clearly see that if we let, so the acceptance region so that's the region which you accept the null is going to be x bar minus y bar is going to be less than or equal to z alpha over 2 and then negative z alpha over 2. Okay. And you can easily convert that into So you can easily convert that into a 1 minus alpha times 100% confidence interval for mu x minus mu y. Which is just okay, so this just essentially what we're doing is just we're using the concepts from chapter 9 to translate between the acceptance regions and the confidence intervals here. And then as an exercise, find acceptance regions and 1 minus alpha times 100% confidence intervals for one-sided alternatives. One-sided alternatives, mu x bigger than mu y and mu x less than mu y. So this again should just use the concepts that we've learned in previous chapters. In chapter 9. So I'll leave that as an exercise for you. That's also kind of a good review of material in chapter 9. So the next question is, what if sigma x squared, sigma y squared is unknown, which is often the case in practice. So we're gonna, make the simplifying assumption. I'm gonna talk to you shortly about how you can actually sort of test that as well. Make the simplifying assumption that sigma x squared equals sigma y squared equals sigma squared, but it's unknown. Okay, so you have okay, so we already know that from earlier, we already know that that this is the distribution of like the x bar minus y bar, where we subtract off the mean and then divide by the square root of the variance. And then if we have sigma x squared equals sigma y squared equals sigma squared, then we have sigma times square root of 2 over n. Okay, but sigma is unknown and it needs to be estimated. Okay, and so how are we going to estimate that? Well, so we kind of have a few options here. So we have the statistics sx squared. Okay, so we know that that's an unbiased estimate for sigma x squared, and which is sigma squared. Okay, and so ideally want to use both sx squared and sy squared to estimate sigma squared, so that we exploit data as much as possible. Okay, and so this leads to the pooled estimate of sigma squared, which we're going to call sp squared. And so what that is that's just a linear combination of sx squared and sy squared that kind of makes things unbiased and takes the best advantage of the data. And it's reasonably intuitive. It's just okay, so this is just a linear combination of sx squared and sy squared, and you essentially multiply this by n minus 1 and m minus 1 to make sure that things kind of work out, and that just comes from the formulas that we have here. So you can kind of write it out fully. So we know that okay, if we expand out, then what we notice is that so sx squared we know is 1 over n minus 1. Xi minus x bar squared. And then we know that sy squared is 1 over m minus 1. Okay, and so what we then can say is that if we look at n plus m minus 2 sp squared over sigma squared, this is going to be useful because it's going to allow us to derive the distribution of this statistic. That's going to equal to n minus 1 sx squared plus m minus 1 sy squared, all divided by sigma squared, which is equal to 1 over sigma squared and then summation plus and so this, as we know, is okay, and we know that this is chi squared n minus 1. We know that this is chi squared m minus 1. And then we also know that they're independent because the samples themselves are independent. So therefore we have that n plus m minus 2 sp squared over rho squared. That is distributed chi squared, where the degrees of freedom now are n plus m minus 2. Okay, and so this kind of makes intuitive sense. So this notion of the chi-square distribution and degrees of freedom is going to be very important for the remainder of the course. We saw it come up a little bit in the hypothesis testing section, and it's going to come up a lot throughout the course. So this is going to be assumed as like degrees of freedom. So the interpretation is that you have n samples x1, x2 up to xn, and then you have m samples y1, y2 up to ym. Okay, and then so that's therefore that's n plus m degrees of freedom. And then you lose 1 for x bar, because kind of x bar uses the n samples in a different ways, and then you lose another for y bar. So this is a little bit intuitive, but I'm just trying to give some explanation as to why that's that n plus m minus 2 is there. So normally when you only have one sample, you see the chi-squared has n minus 1 degrees of freedom. And the reason for that is because you lose 1 degree of freedom from x bar. Because we have 2 samples here and we've got x bar and y bar, you lose essentially 2 degrees of freedom, 1 for x bar and y bar. So therefore, m plus n minus 2 degrees of freedom. Okay. The other thing that's fairly straightforward to show is that E of sp squared just equals to sigma squared. You can just do that calculation yourself because it's just it's a linear combination of x squared and sy squared. Okay, and so so just returning to what we already have. So we know that sigma times square root of 2 on n, that's normal, mean 0 and variance 1. And then therefore we have that you can potentially guess what's going to happen here. We're going to replace the sigma by s rho, square root of 2 over n. But then what happens to the distribution rate? So when you typically do this, a normal will become something like a t distribution, and that's exactly what's going to happen here. So we can re-express this now as and then that's all going to be over the square root of 2 sp squared over n sigma squared. And so you can see that that whole thing is going to be just when you kind of do the appropriate cancellations, that's just going to be t with n plus m minus 2 degrees of freedom. So therefore, the in this case, this the test statistic is a t now instead of a z. So is this t, which is so let me just put it into a testing framework again. So so what we have then is our h naught is mu x minus mu y equals 0, and then we have our 3 different alternatives: mu x minus mu y not equal to 0, mu x minus mu y greater than 0, and then mu x minus mu y less than 0. So so you can see then that the test statistic, so under h naught, we have that t is equal to x bar minus y bar. So under h naught means that mu x minus mu y equals 0. And then we divide this by sp times square root of 2 over n. Okay? And we know that that's t n plus m minus 2. So now, this leads to the, the overall t-test. So this is the t-test for two samples. Okay, and so what we have there is that if we think about the acceptance region, here the size is alpha, then we get that under the first alternative, which is two-sided, we're going to have t is in negative t n plus m minus 2 alpha. I'll draw what these two areas look like shortly. N plus m minus 2. So this is alpha over 2 again, and alpha over 2. For the alternative where mu x minus mu y is bigger than 0, we get t is less than or equal to t alpha, or t n plus m minus 2 alpha. And these are something you can just look up on a t-table. And for t, this is going to be equal to negative t n plus m minus 2 alpha. So remember that the t distribution here is essentially it's like the normal but with slightly fatter tails. And so this is t alpha, this is negative t alpha. And so this is what we get for our acceptance regions. And this also can translate into 1 minus alpha times 100% confidence intervals for mu x minus mu y. And I will only do this for the first example, for the two-sided alternative. You can convert that acceptance region straight into a confidence interval. That's just going to be x bar minus y bar plus or minus, and then it's going to be t n plus m minus 2 alpha over 2 times sp square root of t over 2 over n. Okay, so this gives you, and then as an exercise, find 1 minus alpha times 100% confidence intervals for alternatives, these one-sided alternatives 2 and 3. Okay, so that kind of gives you an idea of what to do when the variance is unknown. And I'll just quickly mention, we can test so one of the assumptions here that we made was if sigma squared equals sigma y squared, and then this is going to be done using an f-test. I'm only going to skim over this because we're going to see the notion of f-test come up a lot more in later chapters when we start to talk about analysis of variance and where we're actually going to be really interested in comparing variances. So one thing to note is that we have that if we have the statistics sx squared and sy squared, what we know is we know that n minus 1 sx squared over sigma x squared is chi squared n minus 1. And then we also know that m minus 1 sy squared over sigma y squared is chi squared m minus 1. Okay, so like if we have our h naught, which is that sigma x squared equals sigma y squared, which is equivalent to sigma x squared over sigma y squared equals 1. And then our alternative is that sigma squared's not equal to sigma y squared, which is, again, that sigma x squared over sigma y squared is not 1. Okay? So then what we can see is if we look at the ratio of, if we consider the test statistic where you might just naturally compare the ratio of these two, and if it's far away from 1, you reject null, and if it's close to 1, then you accept the null hypothesis. Then what you can see is that under h naught, which is that sigma x squared equals sigma y squared, we have that sx squared over sy squared has the distribution of, so let me just write this out more explicitly. So that just equals to n minus 1 sx squared over n minus 1 sigma x squared. And then we divide that by m minus 1 sy squared over m minus 1 sigma y squared. Because sigma x squared over sigma y squares cancel, this is just going to be equal to, so we can just write this as sigma squared and then sigma squared. And so this is going to have the distribution of chi squared n minus 1 over n minus 1 over chi squared m minus 1 over m minus 1. And these are independent again because the samples are independent. And so this is going to have the distribution f n minus 1 m minus 1. Okay, so we have that our under h naught, sx squared over sy squared is f n minus 1 m minus 1. And so then we can use f table to determine is close or far away from 1. And remember, this is going to be a two-sided test, so essentially, like, the f statistic kind of looks something like this, or the f table looks something like this, and so we're going to be interested in this area being kind of alpha over 2 and alpha over 2, and this is going to be like your say f1 and f2. So we're going to accept h naught if that f statistic that we have is between these f2 and f1, and that depends on the degrees of freedom and obviously the alpha that we have. So I should say so if our statistic is between these two thresholds, then that can tell you whether your variance is close to 1 or not. Or the ratio of your variances, is close to 1. So in many cases, your x's and y's are paired, and this is a bit different from the what we saw earlier, where you might just take a random sample of size m from one state and size n from another state. You might have examples where things are paired. So for example, let's consider mother and daughter heights, and you're trying to test whether our daughter's taller or smaller or shorter, I should say, than their mothers. Okay, and so here, these are clearly paired because mothers and daughters basically come as a pair. I mean, you could certainly look at a population of mothers and a population of daughters if you wanted to, but you're kind of ignoring the information that clearly a taller mother is more likely to produce a taller daughter, and vice versa. And so this is where the information's kind of paired. So here your data is actually x1, y1, x2, y2, xn, yn. And so the idea here is that xi not independent of yi, not independent of yi. And if you think about the mother-daughter example, that makes sense. Like clearly, as I mentioned, a taller mother is more likely to produce a taller daughter, so you expect some sort of dependence there. Xi is not independent of mu I, but the xi, yi pairs are independent. Okay, and so you can imagine that each mother-daughter pair is independent, but each mother, like the mother and daughter together, are certainly not independent. So the idea here is that essentially you have something like that expectation of xi equals mu x, the variance of xi equals sigma x squared, e of yi equals mu y, and the variance of yi equals sigma y squared. And then for simplicity, we're just going to assume sigma x squared equals sigma y squared, as I mentioned earlier. So we're just going to call this sigma squared. And then we also have that the correlation between xi, yi is equal to rho. And, that's often going to be bigger than 0, just because, if you think about the example of mother and daughter heights. And so to take a concrete distributional example, here you have a set of variables that are dependent. So you might have that xi, yi is bivariate normal. So I'm just going to use the notation bivariate normal with the means mu x, mu y, variance sigma x squared, sigma y squared, and the correlation rho. And this is for independent. So they're not independent of each other, and this is an important distinction to understand here. They're not independent. The x's and y's are not independent of each other because they come from a joint distribution that's the bivariate normal. But each of the pairs are independent. And so once again, we're interested in the same question. Same question. We want to test whether mu x equals mu y. So once again, in the testing framework, you could have that h naught is that mu x minus mu y is 0. So this is your so mu x minus mu y is your parameter of interest. And then you have that H1 is, we have the three alternatives that we might be interested in. Mu x not equal to mu y, mu x minus mu y bigger than 0, and mu x minus mu y less than 0. Okay, and so one option is to do a two-sample test like we did before. So, there you have that clearly, the statistic there is x bar minus y bar over SP times square root of 2 over n. One of the issues here is that, but since, xi and yi are correlated or, dependent, the SP squared is, no longer chi squared in the normal case. And more importantly, like you could certainly do this and it's not a horrible thing to do, but more importantly, we are not exploiting the correlation between xi and yi, and this is really important because we know that mothers and daughters' height should be related, but we're not really, like in the two sample test, we're kind of treating it as though we have a population of mothers and a population of daughters. Really, when you have a set of pairs, that's more information than what you had in the previous example, and you might want to actually kind of use that. Another scenario you might think of is that, for a control and treatment group, maybe there's actually like, you can use the same individuals for the control, then perform the intervention, and then see how they react to that. And that's another scenario where your samples would be paired too. So this is where we're going to use differences. So we're essentially just going to let di equal to xi yi. Okay, and now we have just one data set, which is, D1, D2 up to Dn. These are independent because the xi and because the xi-y pairs are independent. So since the xi yi pairs are independent. And then the other thing to note is that, so then what we could do is just we could do a test on, now it just becomes, we could do a standard one sample t-test, right? So we have that mu d, which is equal to mu x minus mu y. That's the difference. We now just have one, h naught is that mu d is equal to 0, and then we have the various alternatives. And then we can, use our test statistic d bar, which is 1 over n summation I equals 1 to n di. And then we could also have that sd squared is just 1 over n minus 1 summation I equals 1 to n di minus d bar squared. And so you can do kind of a standard t-test. So if you let t equal to d bar over square root of sd, or I should say sd over square root of n. And clearly, if you assume that xi, yi's are normally distributed, then t is going to have the distribution t n minus 1. So I'll just do it in the case of h1, which is this alternative that mu d is not equal to 0. The other two I'll leave as an exercise again. You can see that under h naught, t is equal d bar on sd over square root of n has a t distribution with n minus 1 degrees of freedom. And so the acceptance region for t is t is going to be between t n minus 1 alpha over 2 or negative of that, and then t n plus 1 alpha over 2. And similarly, you can if you want 1 minus alpha times 100% confidence interval for mu x minus mu y, that's going to be mu x minus mu y is in d bar plus or minus, and then it's going to be t n minus 1 alpha over 2 times sd over square root of n. Okay, so this is how we do things when we look at pair differences. Now, a natural question you might ask is, why is this better than doing a standard 2-sample test? And so this is where we're going to kind of exploit the correlation structure between x and y. Or you could even ask, is this better than doing a 2-sample test? So remember that, so di is equal to xi minus yi here. So we know that expectation of di is mu x minus mu y. But then if we look at the variance of di, that is equal to, I'll just write this out. So it's the variance of xi minus yi. It's the covariance of xi minus 2 times the covariance of xi yi plus covariance of yi. And, if you write that all out, that's going to be sigma squared minus 2 sigma times sigma squared times rho plus sigma squared. And so this whole thing is going to be 2 sigma squared times 1 minus rho. Okay, and so what that means is that therefore we have that the expectation of SD squared is equal to 2 sigma squared times 1 minus rho. So if rho is positive, then E of SD squared is going to clearly be less than 2 sigma squared. Okay, now let's go back to the paired samples here that we have here. Or let's go back to the two sample case. In the two sample case, we have that our confidence intervals would be, so if we have 1 minus alpha times 100% confidence intervals, then we're going to have that mu x minus mu y is in x bar minus y bar, and then plus or minus, and then we're going to have t, and then m, it's a little bit different, or we'll say, because we have m equals n, so we've got m equals n here. We're going to have 2, and then the degrees of freedom become 2n minus 2 alpha. And then, so there's a little bit of a difference there, but it doesn't make a huge difference. And then this is going to be times SP times square root of 2 over n. Okay? So we know that the expectation of SP squared is sigma squared over n. So you can see that, therefore, if we look at here, we have, E of SP squared times, E of SP squared is not sigma squared over n, it is, it's sigma squared. So E of SP squared is sigma squared. And so, therefore we have that mu x minus mu y is effectively in this confidence interval. And then, we'll say sigma times square root of 2 over n. And then for the paired samples, we have that mu x minus mu y is in d bar plus or minus t n minus 1, and then we're going to have something like sigma times square root of 1 minus rho times square root of 2 over n. So this is kind of approximately the payoff that you get. So therefore, if we have positive correlation, as we would with the case of mothers and daughters, we get tighter confidence intervals. One thing to note here is that we have that it is straightforward to show that d bar is equal to x bar minus y bar. Okay, so this was just demonstrating that the paired sample test and the two sample tests are a little bit different, and it's really important to know which setup you're in to kind of address the question of whether you should use a two sample test or a paired sample test. So just to give an overview of chapter 11. So we have, now our data now consists of either two samples or two independent samples. X1, X2 up to Xn, and then Y1, Y2 up to Ym. And then we have, or the second case of paired samples. This is Xi, Y, X1, Y1, X2, Y2, up to Xn, Yn. And so then so you can think of this as component one of the framework. The model slash parameters. In the first case, we have xi as normal with mean mu y sigma squared. We looked at the case where they could be different, but for simplicity, we're interested in the case where they're the same. And so in the second case, we have that xi yi is like a bivariate normal mu x mu y sigma x squared sigma y squared rho. And the thing to bear in mind is that it's straightforward to extend to non-normal case, just as we did in chapters 8 and 9, where distributions of statistics become asymptotic. So everything basically stays the same, but our distributions, obviously, you don't have this nice closed form representations of the distribution like we do in the normal case. And so the parameter of interest here is like mu x minus mu y. And then if we have a statistic, in case 1, it's going to be x bar minus y bar. And then you could also, have that rescale to be sp times square root of 2 over, or and then in the second case, we have d bar over sd times square root of 1 over n. And then the distribution of statistic. And this is all under h naught. So this has this t distribution, and then we also have a t distribution in the second case. If the variances is known, these just become normal distributions. Okay, and then 5 for the analysis. We just follow the testing framework, or confidence intervals. Confidence intervals from chapters 8 and 9. Okay, and so that kind of gives a summary of what we've learned in chapter 11, which looks at the scenario where we have two independent, where we have 2 samples. And we're going to look at other kind of more interesting cases going beyond 1 sample next week. Okay, thanks very much. That's it for today.